In the early 1970s, the United States Navy was developing a new generation of submarine and surface ship fleets. Testing their sonar transducers required an immense amount of high-stakes acoustical data, but researchers hit a bottleneck. Testing was stalled by manual, labor-intensive data collection and disparate hardware systems that couldn't communicate. To get a single reading, engineers had to write separate text-based code for every unique instrument. Dr. James Trishard, or Dr. T, viewed this inefficiency through the lens of a Texas farm upbringing. Having grown up without indoor plumbing or electricity, he prioritized adaptability and practical problem-solving. When he realized university hierarchies would take decades to navigate, he moved his work to his garage, co-founding National Instruments in 1976. At that time, the barrier wasn't a lack of scientific ambition, it was the lack of a system that could organize and standardize physical data. Trishard's solution was virtual instrumentation. He wanted to replicate the logic of a physical hardware panel entirely within software, aiming to make test and measurement as accessible as a financial spreadsheet. This led to the launch of LabVIEW in 1986. It allowed domain experts, from astrophysicists to mechanical engineers, to build custom test applications by connecting visual, graphical icons with software wires, rather than writing thousands of lines of text-based code. The software became a standard for zero margin for error missions. NASA utilized LabVIEW to synchronize the 250,000 microshutters on the James Webb Space Telescope's spectrograph, firing them 240 times per minute during critical environmental testing. At CERN, researchers deployed the same framework to manage the massive data throughput and complex timing required to control the Large Hadron Collider. Trishard didn't just release a product, he built the framework that manages real-time data for the world's most complex engineering initiatives. While many technology firms optimize for quarterly earnings and short-term market reactions, National Instruments followed a path defined by long-term structural integrity. Trishard instituted the 100-year plan, a philosophy that prioritized multi-decade stability and employee well-being over immediate shareholder returns. He believed corporate culture was a key operational differentiator that required its own architectural planning. This timeline shows the steady, iterative growth of the company. It reflects Trishard's OOCH approach to innovation, achieving breakthroughs through continuous, incremental steps, rather than unstructured disruption. He compared this method to a small domino eventually knocking over larger ones. He maintained this culture through sneaker management, frequently walking the corporate campus to speak face-to-face with engineers and staff, bypassing traditional executive barriers to stay connected to the actual work. Trishard treated the corporation as a complex system that required the same rigorous, long-term engineering as the software it produced. Trishard describes his philanthropy as an intellectual investment. He targeted multi-million-dollar endowments at Texas A&M, Rice, and UT Austin to fortify the Texas engineering pipeline, the same ecosystem that provided his company's talent. At the University of Texas at Austin, his $10 million gift funded a massive student makerspace. The goal was to ensure students learned by actively building systems, from solar cars to robotics, rather than just studying theory. This decades-long focus on resilience culminated in late 2023, when Emerson Electric acquired National Instruments for $8.2 billion in cash. Trishard held his millions of shares until the end, executing 0 trades in his final 5 years at the firm. This steadfast position returned him to the billionaire ranks and validated the logic of his century-long roadmap. This multi-billion-dollar exit served as the final proof of a corporate system designed 50 years in advance. After 40 years in automation, Trishard turned to neurodegenerative research. He found a field in crisis. Despite tens of billions spent, the scientific community has struggled to move closer to a cure for Alzheimer's. To Trishard, the biological field looked familiar. It was the same landscape of isolated hardware and incompatible data he had seen in 1976. Over 130,000 peer-reviewed papers have been published, but the research is trapped in narrow silos. Most funding is concentrated on a single hypothesis, leaving the broader biological data fragmented and disconnected. The problem isn't a lack of raw information. It's the lack of a systems-level synthesis to bring the data together. Truchard established the Oscar Fisher Project to change the incentives of scientific research. He moved away from traditional charitable models, instead using targeted capital to reward the synthesis of existing information. The Oscar Fisher Prize provides $4 million to researchers stepping back from their own silos. The challenge is to take this massive cloud of fragmented literature, force a cross-disciplinary look at brain network disruption, and condense it into a single, cohesive explanation. This approach mirrors Truchard's personal life as a native landscape gardener. Over decades, he transformed a rocky, bare lot into a complex, thriving ecosystem by focusing on the long-term health of the entire environment. Dr. James Truchard spent 4 decades standardizing the tools we use to measure the physical world. Now, he is applying that same methodical patience to finding a systems-level answer for the human brain.